All right, so let's start to talk about this Gaussian random process. So a real random process xt is Gaussian if all if for all positive integers n and uh, for all t1, t2 to tn, the random vector is a Gaussian random vector. So let xt in index at t1, t2 to tn will be xt1, xt2, xtn. And then by convention, we always like to use a column vector. So we take a transpose. So we can see it this way. You have a Gaussian random process and you index it at t1, t2, t3, t4, so on and so forth. So you get a xt1, xt2, xt3, etc. So that is a Gaussian random vector. In other words, the random variables are jointly Gaussian random variables. Similar to jointly Gaussian random variables, linear filtering of Gaussian random process results in a Gaussian random process, even when the filter is time varying. So if we recall something here, a process passed through a LTI system has this property. Furthermore, if it's Gaussian, then it's even better, easier to deal with, because when it passes through a system, the outcome is a Gaussian random process. And two real random processes x and y are jointly Gaussian if for all positive integers n, then all the time index t1, t2 to tn and t1 prime, t2 prime to tn prime, the random vector, notice that x is indexed by t1, t2 to tn, and y is indexed by t1 prime, t2 prime to tn prime, and that t1 may not be the same as t1 prime, t2 may not be the same as t2 prime, and even their index is not the same. Okay, so you imagine we have a process, two process, one index here, and then the other being indexed similarly, but the time index may not be one-to-one correspondence. Okay, index. And then you index a lot of samples, and in fact, when you take index, it's not samples, it's random variables. When random variables are realized, they are called realization or samples. So, but for now, we use the vocabulary random variable. So you have random variable x, 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 and y, 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 etc. Has to be a Gaussian vector. For two jointly Gaussian random processes, xt, yt being uncorrelated, that is, we have rxy t plus tau t is equal to aspect of xt plus tau yt for all t and tau. So what that means is if you take x, you take x at t plus tau and you take y at t, the expectation is the individual expectation multiplied. So let's say you take the expectation correlation of this at t, you take another correlation with another symbol at t plus tau. What happens is it's equal to expectation of this individually. You take expectation of this individually, and then take expectation of this separately, and then multiply together. So that will be the correlation. If that property sustains, then they are uncorrelated. And then, of course, for Gaussian, uncorrelation represents independence. So that's independent. A complex process Z equal to xt plus jyt is a Gaussian if xt and yt are jointly Gaussian process. Okay, that'll be Gaussian random process. Then Y process. A process is called a Y process. This is a bit abstract, but it's very important because it often occurs in the noise process. In the noise process, so we pay we pay a little bit of more attention on this Y process. Okay, so let's look. A process is called a Y process. Its power spectral density is constant for all frequencies. The constant value is usually denoted by n or n0 over 2. So do it this way. xxf equal to n0 over 2. Using equation, we see that the power in the Y process is infinite. This is just too strange, right? But see it as an approximation. See it as an approximation. Okay, let's look how this is going to happen. A Y process is what? You take the power spectral density and it's constant for all frequency. Recall that power spectral density is a Fourier transformation of autocorrelation, right? It's a autocorrelation of a autocorrelation. Then how come uh, it's a constant for all frequency? If let's recall, if in frequency domain a process has flat frequency, a flat energy for all frequency, then what's happening is its time domain. Its time domain behavior must have been something like an impulse, right? It has to be something like an impulse. Then how come autocorrelation is an impulse? It just means that this process is correlated with itself only for tau equal to 0. For tau non-zero, it has no correlation. So that its autocorrelation is like it's like no, I'm sorry. So that it will be like something like that, impulse. Okay, so it's a Y process for all frequency. Then constant value is usually denoted by n0 divided by 2. So, but it's just a notation. So we will have sxf equal to n0 divided by 2. So we will see that power in the Y process is infinite, indicate that a Y process cannot exist as a physical process. Well, so in fact, if you see it far enough, it's in fact like a Y process, but gradually in F very, very further away, it still decreases to zero. That's reality. That's in reality. It still decreases to zero. But however, in a range we're interested is like a flat constant, n0 divided by 2. So that is the um, what we call Y process. And I want to bring to attention that Y process is flat in F and then it's an impulse in T. But how come it's an impulse in T? That means that the process itself uh, it's only related to itself in time difference equal to zero. If you shift it a little bit, you take the expectation with this one and this one, then they are very uncorrelated. In other words, in other words, what we actually see is sample between sample and sample, their correlation is zero or close to zero. What that means is you are going to see a process that varies a lot. It varies a lot. So when you take sample with respect to sample, they are uncorrelated. It's not like the thing I draw here. You can see that this is correlated with this, is correlated with this, is correlated with this. But if you are going to see a, a very so-called Y process, you're going to expect things that are like this. It changes very fast without correlation. Not even sinusoidal. I'm not talking about high frequency sinusoidal. It has no relationship. Not even sinusoidal, and not even polynomial, not even anything. It's just uncorrelated. Okay, so that is a called Y process. But okay, so hopefully that you understand this, and there will be some explanations in physics about this. Okay, although Y processes are not physically realizable process, they are very useful, closely modeling some important physical phenomena, including thermal noise, including the thermal noise. So previously we say we have a Tx, we have a Rx, and we have an antenna that gives you transmission, and ambient noise that comes in. Ambient noise that comes in. Some of them are interference, and some of them are thermal noise. That is just exists in the universe, in the atmosphere. Those things are called thermal noise, and they come from the dynamics in the physics, in the physical world, and they are usually hard to deal with, and we model it by white noise. So oftentimes you will see that a process ST equal to the signal you are transmitting and then plus the noise N, right? And we model it by white noise. This term, we model it by white noise. If you see some communication literatures, you're going to see this a lot. So thermal noise is a noise generated in electrical devices by the thermal agitation of electrons. Thermal noise can be closely modeled by random path NT, having this property. Okay, so it's a stationary process. It's a zero mean process. It's a Gaussian process. It's a Y process with power spectral density given by this. So T is the ambient temperature in Kelvins and Boltzmann's constants, so on and so forth. But uh, the point is flat. Okay, okay. Then let's talk about discrete time random process. discrete time random process has similar properties to the continuous time process. In particular, the power spectral density of a wide-sense stationary discrete time random process is defined as a discrete time Fourier transform of its autocorrelation function. So this is a DFT, discrete uh, discrete time Fourier transformation. So if you have an autocorrelation function that is discrete Rxm, what that means is uh, it's a discrete time, meaning that its value is defined only in discrete instance. So for example, you have a point here, you have a point here, you have a point here, a point here, a point here, a point here. So you imagine you have a continuous process and taken at discrete times. And for samples out of those discrete time instances, they're undefined. We, we should not say anything about that because otherwise we're assuming extra information, and that should not happen. So it will be this sample and this sample, and this Rx is the correlation of this sample with respect to this sample. That will be T two time instance, right? Two time instance. That will be R2. That will be R2. But of course, we can change that, right? So you can take this with this, take this with that, and then you get different values of that is the autocorrelation function of X. And then what happens is you do Fourier transform in the discrete version. In the discrete version, so Sx f is equal to this, and this is a typical discrete time Fourier transformation. And the autocorrelation function can be obtained as the inverse transform of the power spectral density. So if you have Sxf, then you take the inverse E j 2 pi fm, then take df. Discrete time Fourier transformation has a circular behavior in time domain, so we only have to take a finite period in one period, right? Recall signals and systems. We take this f within one cycle, which is from minus one half to half to one half, and it's Rxm. Okay, so you get inverse. The power in discrete time random process is given by you take the expectation of xn squared slot p, which is equal to R of 0. In other words, if you have a random process, you are taking with respect to a specific time, and of course it's stationary. So if you take this, it's equivalent to if you take this. It's equivalent to if you take this. Remember, we are taking expectation for random variable, not realization. So you have expectation of this, and with respect to itself, so that is Rx0, time difference equal to 0. And that is for one cycle of the spectral density, just one cycle, and it's vector of xn squared. It's y-sense stationary, so for any time instant, you get the same, get the same outcome. So regardless of the n. Okay, so that would be for our y process and also discrete time random process. All right. Then let's skip some subsections and go to a, a property, a point that is more relevant to our communication engineering. Okay. So we are going to this series expansion of random process. So series expansion of random process results in expressing the random processes in terms of a sequence of random variables as coefficients of orthogonal or orthonormal basis functions. This type of expansion reduces working with random process to work with random variables, which in many cases are easier to handle. Okay, so when we talk about series expansion, you recall if expansion or transformation is always about basis. And what is a basis? As we did, Fourier transformation is the basis on exponent, right? Exponent of something, that is the basis. And Taylor expansion is another kind of basis, right? Taylor expansion. So series expansion, we want to represent the random process in terms of a sequence of random variable as coefficient of orthogonal and orthonormal basis function. So in other words, if we have a random process, we like to represent it as what? As for example, this is the basis, a set of bases, right? A set of bases. Then of course, basis has a well-behaved behavior because they are orthogonal and orthonormal. They have nice properties, right? And you want to represent this as what? As A multiplied by this, and then B multiplied by this, and then C multiplied by this, so on and so forth, so on and so forth. We'd like to represent this with respect to a combination of this with coefficients. And then where the randomness go to? You have randomness in your random process, right? This is no longer a deterministic function anymore. So what happens is the randomness goes to the randomness in ABC. Let me put it slowly and say it again. So think about it. You have a random process here. The random process has randomness in it, but you want to represent it by a basis. Then randomness are not supposed to be gone, right? They have to be somewhere in the representation. Therefore, randomness goes to the coefficient, which we model coefficient as random variables. That represents the randomness in here. However, the basis is deterministic. That is orthogonal or orthonormal. Okay, so that's like Fourier transform or Taylor expansion, something like that. So this kind of expansion reduces working in random process to working with random variable, which are easier to handle. So we are going to describe uh, series expansion for random process. Okay. Okay, I think up to this point, we take a break and go back.